We are starting to work on some derivatives of functions that involve trig functions. So one of the things that we've done is we've made a list of the derivatives of the trig functions. So we had this little table where we have a function and then its derivative. So for example, we've learned that if the function is sine of x, the derivative is cosine of x. And if the function is cosine of x, the derivative is negative sine of x. And if the function is tangent of x, the derivative is secant squared of x. Secant of x, the derivative was secant x tangent x. Cosecant of x is negative cosecant of x, cotangent of x. And then finally, the cotangent of x is negative cosecant squared of x. And you were introduced to these formulas in another video. In particular, something I want to point out is the functions that start with co have a negative derivative. So cosine, cosecant, and cotangent have negative derivatives, or a negative sign in the formula anyway. And then for sine, tangent, and secant, there's no negative sign in those. So pay attention to those as we are working through these problems. These are just the formulas for the derivatives, remember. They're going to come in handy for the problems that we're going to encounter. We've also found out that we need to be aware of some of the trig identities that come from your study of trigonometry. And I want to remind you of some of those here. These are just some basic facts that are important to know when you're working with trig functions. So first of all, I want you to know that all of the trig functions can be written as some form of sine or cosine. For example, the tangent of x can be rewritten as the sine of x over the cosine of x. That's a standard identity that everybody learns in trig class. The secant of x can also be written in terms of just cosine. That's 1 over the cosine of x. The cosecant of x is 1 over the sine of x. And the cotangent is just the reciprocal of the tangent. So I could write that as 1 over tangent, but more importantly, it's the cosine of x over the sine of x. It's the reciprocal of the tangent. And then the other important identity that everybody should remember from trig class is the Pythagorean identity, which says that the cosine squared of x plus sine squared of x equals 1. That's a famous one, and we can actually transform that into a couple other Pythagorean identities too, but this one's the famous version of the Pythagorean identity. And as we're working through our problems, these identities might come up, and I just wanted you to be aware that we're going to refer to these. You have a goldenrod packet that has a whole bunch of other trig identities, so keep that thing handy because you might need to refer to it as you're working through our problems. Let me just introduce you to a few examples that will be similar to the problems you're going to work on this first night, and then we'll go from there. So the first problem I want to take a look at is this function y equals 7 over x plus 4 sine of x. And our job is to find the derivative. So before we do that, let's rewrite this expression in a form that is useful for what we know. The only thing we really know is the power rule, the e to the x rule, and now these trig function rules. So we need to write this in one of those forms. So I'm going to turn 7 over x into 7x to the negative 1. And then the 4 sine of x we can just leave. That's just a constant multiple of sine of x. From here, this derivative shouldn't be too bad. So y prime, which is the derivative that I'm looking for, is going to be, I'm going to do a power rule on this thing. So that's going to be negative 7 x to the negative 2. Remember, you bring that negative 1 down, multiply by 7, and then subtract 1 from the exponent. A lot of people try and make that 0, but negative 1 minus 1 is really negative 2. Plus, this 4 is a constant multiple, so it's just going to hang around and multiply by whatever the derivative of is of sine of x, which we already wrote on the last slide was cosine of x. So we're essentially done with this thing. The only thing I would recommend is that we write the answer in the same form as the original problem posed, and that means write this as with a positive exponent. So my final formula for the derivative of y is going to be negative 7 over x squared plus 4 cosine of x. That's probably how we should write that answer. Negative 7 over x squared plus 4 cosine of x. And for some of the problems that we work on tonight, it's just going to be as simple as incorporating those trig functions the way we did before. Okay, let's take a look at another example. So in example 2, we're going to look at the function y equals secant of x times the quantity sine of x plus cosine of x. There's a couple of different ways to attack this problem. One way would be to imagine this as a product where it's the secant of x times the sine of x plus the cosine of x. And you could run through the product rule to do that. But what I want to do is I want to just use the distributive property to multiply this out and then use some of our trig identities to transform this into a really easy derivative. So we're going to multiply this out. And when we do that, some cool stuff's going to happen. I'm going to write it step by step, though. I am not doing the derivative yet, so this is still y. I'm just multiplying this out to write it in a little bit different way. So when I multiply secant of x times tangent of x, or excuse me, sine of x, I get that product plus, and then I'll do secant of x times cosine of x. And I sort of let the cat out of the bag there when I made that slip up. But what I want you to realize is from the last screen, we know that the secant of x is 1 over cosine of x. And if I multiply the secant of x, which is 1 over cosine x times sine of x, I get sine of x over cosine of x. So this really turns into just tangent of x. And again, since this secant of x is 1 over cosine of x, oopsie, when I do 1 over cosine of x times cosine of x, I just get 1. And so this is really just tangent of x plus 1. I still haven't done the derivative. I've just transformed this expression into a simpler form by multiplying everything out and using my trig identities. Now, at this step, I'm ready to do the derivative, and this is just what I would call a slam dunk. The tangent of x, the derivative of tangent of x, is right off our chart. That is the secant squared of x. And the derivative of 1 is 0, so I'm done. The answer to this particular derivative problem is secant squared of x. Rather than run through the product rule, what we did here is we used our multiplication and our trig identities to simplify the expression so that it was in this form here, and then the derivative was pretty straightforward. And that's one technique for doing this problem. Okay, let's take a look at another example. In example 3, we're going to find the derivative of 8 over tangent of x plus 3 over sine of x. Now, at this point in our class, we have not learned the quotient rule yet. So we're going to try and avoid writing these as fractions, and instead, we're going to rewrite this expression without the fractions. To do that, I have to remember what 8 over the tangent of x really equals. This is really the product of 8 and 1 over the tangent of x. And 3 over sine of x is really 3 times 1 over the sine of x. And these guys are just part of our identities. So I can rewrite this formula. I still haven't done any calculus yet, but I can rewrite the formula as 8 times the cotangent of x, because 1 over the tangent x is the cotangent of x, plus 3 times the cosecant of x, CSC of x, because 1 over the sine of x is really cosecant of x. So rather than doing the top expression and finding the derivative, we're going to go right to this line, and we'll just use our formula sheet to do the derivatives. For y prime, it's going to be 8 times whatever the derivative of cotangent is. And we have that written down as the secant squared of x. That thing is negative, though, so 8 times negative 1 would be negative 8. So the derivative of cotangent of x is negative cosecant squared x. And when you multiply that by 8, you get negative 8 cosecant squared of x. The derivative of cosecant of x is negative cosecant x cotangent x. So we're going to multiply that by 3, and that'll be minus 3 cosecant of x cotangent of x. Oops. And again, we're done. We used our formula sheet to just do these two derivatives of these trig functions. These are just constant multiples. They just hang around. You stick them on the front. And we're done with this thing. Now, if you're a little rusty with your trig identities, keep that formula sheet handy so that you can rewrite these expressions. What we've done in the last 2 slides is we've used our knowledge of the trig identities to transform a complicated expression into one that's just a simple look at the sheet and write down the derivative problem. So this process in here, all this stuff that takes place between the top line and the third yellow line, that has to do with those identities. And that's going to take some practice if you're rusty on those. Let's do one more problem. Since you hung around to the end of the video, I'm going to do one of your homework problems for you. This happens to be the most challenging of the problems that I have assigned recently. So when I look at this function, y equals the quantity secant x plus tangent x times the quantity secant x minus tangent of x, one way we can think of this is to think of it as a product. And we can run through the product rule with u's and v's on each of these factors and then multiply it all out and simplify it. But another way we can attack this is like we did in one of the earlier examples in the video, which is we can multiply this thing out ahead of time and then use our identities to make it a simpler calculus problem. So what I'm proposing is that we multiply this thing all out using the distributive property. We're going to do secant x times secant x times negative tangent x times secant x times negative tangent x. We're going to multiply that out, right? You probably called that FOIL in algebra class. Since these are conjugates, we're going to end up with a difference of perfect squares. You're going to multiply this all out. The middle terms are going to cancel. And you're going to end up with secant squared of x minus tangent squared of x. And now what I want you to notice is that we don't have a formula for secant squared, and we don't have a formula for tangent squared. So we're not done yet. And what I mean by that is we don't have the derivatives for those. We know the derivative of secant of x, not secant squared of x. And we know the derivative of tangent of x, but not tangent squared of x. So what we need to do is we need to look at our formula, our, identity list, sorry. We're going to look at our identity list, and we're going to use one of those Pythagorean identities to change the way this thing looks. In fact, if you look at your identity list, there's one that involves secant squared of theta. And it says something like this, or secant squared of x. The secant squared of x actually equals tangent squared of x plus 1. And so what I'm proposing is that we replace the secant squared of x with tangent squared of x plus 1. So I'm going to stick that right here. And when I write that out, something awesome happens. I'm going to write tangent squared of x plus 1 minus tangent squared of x. And I think you'll agree that those tangent squares cancel out. And so this function is actually just y equals 1. So this nasty thing up here is really just the horizontal line y equals 1. Let me make my 1 look a little better there. And then for the derivative now, this becomes a piece of cake. The derivative of y equals 1 is just 0 because the derivative of 1 is 0. So that nasty problem that you started with is really just a fancy way of writing y equals 1, and the derivative of y equals 1 is 0. Now, if you'd have gone through the product rule, like I mentioned at the beginning of the slide, you still would have ended up with 0 when you got done. But I think this is a more elegant way to get there, where you write out the difference of squares, use the Pythagorean identity to replace the secant squared of x so that the tangents cancel out, and then just take the derivative of 1 and get 0. this whole trick where we're using these identities is going to take practice. And so we're going to continue to work on this. Don't expect yourself to be perfect at this the first time you try these. And keep your identity sheet handy. And we'll learn to identify the problems that where the identities can help us. So that's good enough for now. Give those problems a shot that I assigned, and then we'll see you soon, and I'll answer your questions. Take care.